complex numbers, modulus and argument. The modulus, or absolute value of a complex number, is the magnitude of its corresponding vector. In other words, it is the length or the distance, we think, from the origin to the complex number along its most direct route. And we write it as such. In other words, it's just Pythagoras. So x squared plus y squared, then square rooted, gives us the modulus. The argument of a complex number is the angle its corresponding vector makes with the positive real axis. One thing to note, it is measured in an anti-clockwise direction. So it moves along the positive axis, and then it is the angle subtended by rotating anti-clockwise to the complex number. So along the positive, anti-clockwise. And we tend to give that in radians. So things that you will need to know for this will be Pythagoras, y squared plus x squared is equal to the hypotenuse squared in this case. Other things to note, basic trigonometry, where y is the opposite, x is the adjacent, so therefore the tangent of the angle is equal to y over x. Noting, positive is in the anti-clockwise direction, negative will be in the clockwise direction. However, we tend to only go through 180 degrees or pi radians. So if we go along the real axis and go anti-clockwise, we rotate round by pi radians or 180 degrees. Alternatively, if we want to go clockwise for the lower angles, we will go from 0 round to pi again or 180, but that will be negative. We will now do some examples. Example 4. Here we have z is equal to 2 plus 7i. So we can quickly think of that as a sketch. Doesn't have to be drawn to scale, but we think of going across 2 and up 7. So this is z, which is equal to 2 plus 7i. Now if I now think of this as a little triangle in here, what do we know? We know that that is 2, that is 7. So therefore, the modulus, written as such, is equal to the square root of 2 squared plus 7 squared. So the modulus is equal to the square root of 53. And it is possible you may be asked to write that in decimal form. Next, so that was part A. In part B, we want to find the argument. So I'm just going to redraw my diagram. Obviously, you could just use the same diagram, but at the moment, I just want us to have it nice and neat. So I think about our triangle. We want to find this angle, noting that we're going in an anti-clockwise direction. So I'm going to call that theta. Noting we have a right angle triangle, that is 7, that is 2, which then means we have tan of theta is equal to 7 over 2. So that means theta is equal to arctan, or the inverse tan, of 7 over 2. So theta is equal to, now at this point it is normal to use radians, so make sure your calculator is in radian mode, and this gives us 1.2924 radians, and it is normal to give this to 2 decimal places, or sometimes 3 SF, so 1.29 radians to 3 SF. And we have our two answers. Example 5. Here we have z, which is minus 4 minus I, and we want to find the modulus and the argument. So, with a quick sketch first of all, we can think of minus 4 minus I, going to be down here somewhere. So we can think of this as being z. Let's just draw that line in. So as far as this as a vector goes, we can think of this as a right angle triangle. We know that that is 1 and that is 4 in terms of the triangle. And obviously in here we can think of that little angle as being theta. Obviously this was with the real axis and the imaginary Okay, to find the modulus then. So the modulus of z is equal to the square root of 4 squared plus 1 squared, which means the modulus of z is equal to the square root of 13. In part B, well, we want to find the argument. An argument is normally taken from the positive real axis in an anti-clockwise direction for positive, only we tend to just go round to 180 degrees or pi radians. This time it's in a different quadrant, so it's in the third quadrant, or first quadrant, second, third quadrant, and we're going to rotate clockwise, giving us a negative angle. And we know that if we come the whole way around to there, that's pi or 180 degrees. So if we can find theta, we can subtract that from it. So tan theta is equal to 1 over 4. So theta is equal to the inverse tan, or arctan, 1 over 4. So theta is equal to 0.2449 radians. But that's not the angle we're looking for. We're looking for the argument of z written as such, and this is equal to, well, if we think we come minus pi, and then we come back theta, so we're going to add on 0.2449, which we keep on our calculator, and when we type that in, we'll get an answer of minus 2.90 radians, and that is to 2 dp as required.